So this is our example, page 178, 179, about pregnancy tests. And we were told out of people who buy pregnancy tests, approximately 10% of them are pregnant. So the chance of someone being pregnant is 10%. Chance of someone therefore being not pregnant is 0.9%. From the test itself, if a pregnant person takes the test, 96% of the time they get a positive result. If a pregnant person takes the test, 4% of the time they get a negative result, a false negative. A not pregnant person takes the test, 95% of the time it shows them as not pregnant, but 5% of the time it's a false positive. But notice this is predicated on knowing the pregnancy status first. So, young woman goes by the test, takes the test, it's positive. What's the chance she's actually pregnant? Notice this is a conditional probability. What is the chance the person is pregnant given that the test was positive? That's not one of the pieces of information we have here. So how can I get this conditional probability from the information I was given? There are two ways based on what we did last time. I could, as we did here, from the tree, build the chart, or I can apply Bayes' theorem. Because what we have here, B and A, are the reverse of what we have here. So I can use this idea and this version of Bayes' theorem. So let's do that calculation. And then we'll do it with the chart so that we can see that it works the same both ways. So if I want to do this, let me just set up the formula. The chance that my person is pregnant given a positive pregnancy test is the chance they were pregnant given positive, the chance they were positive given pregnant times chance of pregnant. I'm reversing the two items. And then on the bottom, I get this again. And the complement shows up in the bottom. So these numbers are available to me in my tree. So let me find them. What is the chance that I got a positive test given that the person is pregnant? That's right up here. That's our 96%. And the chance that the person is pregnant is 10%. So I know the top fraction. .96 times 0.1. Then those same numbers appear on the bottom, but I add the false positive. What is the chance the person gets a positive test but is not pregnant? That's right here. Positive test but not pregnant. Times chance of not being pregnant. What was the chance of not being pregnant? 0.9. So let's multiply. On the top, I get 0.096. On the bottom, I get 0.096 plus what? Which gives me 0.096 over 0.096 plus 0.045, 0.141, which is So here's an interesting note. I have a test that is only wrong either 4% of the time or 5% of the time. You're pregnant, but you get a negative test 4% of the time. You're not pregnant, but you get a positive test 5% of the time. You show me a positive test, there's only a 68% chance you're actually pregnant. Whoa. So there's a 32% chance that test is wrong. How did I get 32 from 4 and 5? Because of the assumption on the likelihood of being pregnant in the first place. Now, this result using Bayes' theorem is not intuitive. And to me, this is an atrociously complicated formula to remember. That's part of why you get a formula sheet for the next exam, because I don't want you to memorize this crap. It's a pain in the ass. But let's do what we did on Monday. From the tree, let's build the chart. So, ignoring this for the moment, let's go back up here to the tree. I really only have two options for each row or column. My person is either pregnant or not. The test is either positive or negative. So I'm going to make a grid this way. Pregnant or not pregnant, we call that P prime, and then a positive or a not positive. So this is pregnancy, and this is the test result. Now I need to fill in those 4 boxes. How do I get the number in this box? From this tree. Numbers in the boxes are joint probabilities. Those come from and. And comes from going out the branches. Mike?
I'll just use the, I guess using those percentages that we got.
Right.
And one of the formulas, the and formula. I would say use the probability of positive given pregnant times the probability of pregnant.
Right, which is the same as saying, oh, I'm going to multiply out this branch. Probability of positive given pregnant times the probability of being pregnant. So that's this branch, and when I multiply that out, 0.1 times 0.96 is 0.096. Hey, that's a familiar looking number. Wasn't that part of our fraction? What goes here? The end of this branch. First of all, what's the number? Second of all, what probability does it represent?
If you are pregnant,
Aha. Probability of negative and pregnant. Wait a minute. Down here, where's that number go? Here. Pregnant and negative result. Notice when we add those two together, we get 0.1, a 10% chance of actually being pregnant. That means this row should total 0.9, so that these add up to 1. And that should make sense because that number is on this branch, and these are all assuming we're negative. Oh, sorry, assuming we are not pregnant. Got to use the right word because negative's up here. So, not pregnant and positive test is what number? Because that's the 0.9 times the 0.05. And the last branch is the probability of not pregnant and a negative test, and that's 0.9 times 0.95. What do I get for that? And notice adding those together gives me 0.900. That's right. Now, what we did in this calculation was to ask for the probability of pregnant given a positive pregnancy test. Ignore all the calculation here. Let's just look at this table. To find the chance that my person is pregnant given that they have a positive pregnancy test, I'm missing 2 numbers from this chart. Yari, which 2 numbers? Bottoms of the columns, right? These 2. But that's exactly the number I want because that's the restriction to being a positive pregnancy test would be the sum of those 2 numbers. So add those 2 up. 0.96 plus 0.096 plus 0.045. Gee, what a familiar sounding number again. And before I go any further, this is the ratio of these 2 numbers. I'm restricting myself to the column that is positive. So I'm only allowed to divide by the 141. I'm looking for the positive part, so that's the 0.096. And that's exactly the number we just came up with, 0.68. So this formula got me that probability without the chart. I think the chart is easier to understand, but the formula works even if I have more than 2 options in each of the parts I've got going on. And that's the better part. The tree diagram gets a lot more complicated when I have more pieces in it, right? The problem we did about carts and payments on Wednesday was exactly that, more options, but I could still do the same calculation from my chart. So I don't think that Bayes' theorem is worthless, but I think in this simple case, it's a lot easier to make the chart. Questions? Talk to me. I'm looking at my notes, by the way. And in my notes, I actually asked a different question. In my notes, I asked, what is the chance that my person is not pregnant given a negative test? So this test we just showed, if you get a positive test, there's only a 68% chance you're pregnant. You get a negative test, chance you're not pregnant. Those 2 are not complementary pieces. This is not the opposite here, because this one isn't working off of this column. It's working off this column. And I didn't finish the numbers, did I? So my real question is, what's this number down here?
0.8.
Aha. And notice again, those 2 add up to 1. But that means the chance of not being pregnant, if you got a negative test, is 0.855 out of 0.859, which is
99.5.
this test is much better at detecting low levels than high levels. If there's even a little bit of a chance you could be pregnant because of well, let me see, medical tech was a long time ago. HCG hormone is present in a pregnant person's body. So if you have any of it, we want to flag that as a positive test. Even though there's a chance we could be wrong, and you could end up with a false positive result. We'd rather be absolutely sure that there's none of it. So this is the sensitive test. Which side would you rather err on? Tell someone they're not pregnant when they are, or tell someone they are pregnant when they're not. That 32% is the chance that I have a positive pregnancy test, but I'm not pregnant. By the way, if you don't like this idea in terms of pregnancy tests, replace this entire behavior with a drug test. All you athletes for NCAA stuff, got to take your drug tests, right? You got to go every couple of however many semesters and go pee in a cup for the NCAA. They do it down in the bottom of the McKenna Center. It's exactly the same idea. Problem number 49 on page 182 is exactly that setting. A drug test has a 5% false positive rate and a 10% false negative rate. Of athletes tested, we're going to make an assumption that 4% actually use prohibited substances for whatever sport that is. If you test positive, what's the chance you're actually doing drugs? Well, you just said there's a 5% false positive rate. Maybe I'm one of the 5%. What's the chance? But what I've got here with this 5% and 10% and this 4% is I've got the ability to write that tree. So in that problem number 49, I have people who use drugs, people who don't use drugs. I have a positive test, I have a negative test. I have a positive test, I have a negative test. We were just told there is a 5% false positive. Where would a false positive go on these branches? I need you to count. Top down, 1, 2, 3, 4. Okay, this would be a false positive. Somebody who doesn't use a prescribed substance, but it shows up on the test. So a 5% false positive means 0.05 when I get there. Chance of a positive test given the person does not use drugs. The 10% false negative, where does that go? They also said that only 4% of athletes are using banned substances. Where does the 4% go? Aha, that would be here, exactly. And that means that this is 96. There we go. Now, that also means I can fill in the other two numbers, the other two blank branches, 0.9 and 0.95. Because each branching set from the same root has to add up to 1. But now I could make the chart and give you all the probabilities in the world you wanted, right? Because I can go here and I can say, oh, either they're a drug user or they aren't. Either they got a positive test or they didn't. And I can fill in the numbers all the way around here. But all of these numbers come from multiplying out the branches, right? 0.04 times 0.10 should be drug and negative test. That should be here. 0.04 times 0.9 should be here. What do we get? And notice that when you add those together, you get 0.04, which is our chance of being on this branch in the first place. Same thing down here. This should be 0.96 when all is said and done, going across. So 96% times 5%, 0.048. And that means that this one, 0.96 times 0.95. And now if I add downward 0.036 plus 0.048 is 0.084. And 0.912 plus 0.004 is 0.916. And now you can give me all the conditionals you want. What is the chance that someone uses drugs given I got a positive test? Again, I restrict myself to the column for the conditional probability. I'm only looking at the plus column. %43%. For a test that's only wrong, 5% of the time one way, 10% of the time the other way, you turn up with a positive drug test, there's only a 43% chance you're actually a drug user. That's a sensitive test. It said, oh, wait a minute, there might be something here, let's catch it. Even if it's not athletes. My wife used to work at a bagel store in Squirrel Hill. And one day she got visited by the FBI. I'm like, what? What do you mean the FBI came to the bagel store? Well, they brought me a picture and they said, do you know this guy? And we said, yeah, he comes in every morning at 8 o'clock in the morning and gets a coffee and a poppy seed bagel and goes. Why? He failed his drug test for opioids. Poppy seeds. But it turns out he was a regular at the bagel store and they knew him by face. They cleared him. I did this problem with Bayes' theorem by looking at all of the conditional probabilities instead. That's the same calculation, but notice where we ended up, 0.036 over 0.084. Exactly the same place. I think Bayes' theorem has its uses. I am much happier to create the chart from it. Questions? As I said, it could be that we have more cases. There is a larger version of Bayes' theorem on page 180. The larger version of Bayes' theorem. I'm gonna have to go through and figure out what the hell this thing means. Yeah, fell off the bottom of the page there. Okay, what the bleep? Okay, first of all, what does mutually exclusive mean? There's no overlap. So each of those events is exclusive from each other. They're disjoint sets. What does collectively exhausting mean? Yeah, well, unfortunately, that would be mentally exhausting, but it isn't collectively exhausting in this case. Collection means the whole sample space. Collectively exhausting means those options are the whole sample space. So mutually exclusive, they're all separate from one another. They have no overlap. Exhausting means they cover all the bases. So mutually exclusive and collectively exhausting. These B's are a complete list of what could happen. In our case, we had positive and negative for the drug test, the pregnancy test. We had pregnant or not pregnant. We had using drugs or not using drugs. Those were exhausting because there were only two options and you couldn't do both. But in our previous example, pay by cash, check, credit card, we had three mutually exclusive, collectively exhausting options because there were really no other ways to pay at that store. Our version of Bayes' theorem that we were looking at before only had two options on the bottom. It either happened A given B or A given not B. But now I have more options. So it's A given the first option, A given the second option, A given the third option, all the way up to A given the last option. We're going through the collectively exhausting part down here. Instead of there only being two, there are now however many it takes to exhaust all the possibilities. This just means more rows or more columns in my branches, in my tree. Therefore, my chart is a little more complicated. The idea is still the same. Again, I'm not thrilled with the idea, but it meant if I had three options, this is the example on page 180. If I had three options, B1, B2, B3, I'm going to need all three of them in the bottom here. Option 1, option 2, and option 3. I still think the chart would be better. We just have 3 rows instead of 2. It would work. Page 182 has some pretty good diagrams on this about how we are shrinking our sample space. And I don't know if you want to think of this set theoretically, but that's just another picture for you. Again, this is why you get a formula sheet, because that's a nasty looking formula. How often are we going to use it? If I can get away with it. Questions? Okay. In order for me to do any of these calculations, I have to have some given probabilities. I have to make some assumptions about what's going on in the world. If I'm doing theoretical probability, that means I need to count my sample space. And I need to count my event to be able to figure out my probability. So I want to talk for a bit about counting formulas. So my theoretical probability formula said the probability of an event is the number of things in the set that is the event divided by the number of things in my sample space S. So S is my sample space, E is some subset of S, that's an event. Some collection of possible outcomes. The best part about this is that the counting rules we use are based off of nothing more than the same ideas we used in our probability scheme. There are really 5 main results I want to get to. Let me start with what I think is the easiest one. I've got 2 options, 2 events that are going to occur. Suppose event A can happen n1, some number, ways. And event B can happen n2 ways. Then both of them happen in the product n1 times n2 ways. Mike, this is exactly what you told me to do earlier. Use the multiplication idea because I'm doing both things, right? Positive and test. Negative and, oh, okay, so I'm doing the and, whenever I see the word and, I'm going to multiply. By the way, this extends to however many you want. Not just 2, it means 3 or 4 or 5 things. If I want all of them to happen, then I can make it happen by multiplying how many ways there are. I hope the following is a direct example, but please note there's an assumption made in here, and we'll get to that assumption in just a moment. What's the state of Pennsylvania license plate look like? You're going down the road, you see a car with a Pennsylvania plate in front of you. What does it look like? They're all formatted the same. That's the color scheme, absolutely. Then there's a set of letters and numbers, right? Okay, so I have letters followed by numbers, and it's 3 letters, and then that silly little keystone symbol, and then numbers. A question for you. How many different ways are there to fill that out? How many different license plates are possible with this arrangement? If I work for the state, I need to know that. Because I need to know when we're going to run out of license plates and have to start recycling them. And then all of a sudden your car and my car might have the same license plate on it. That's a bad thing. So I need to know how many license plates are possible. I need to put a letter in the first slot. How many ways can I put a letter in the first slot? I need to put a letter in the second slot. Third slot. So I have 26 times 26 times 26 just for the left. How about the right side? How many ways to put a digit here? Because I use a 0. So 10. All the way through, right? So I end up with 26 times 26 times 26 times 10 times 10 times 10 times 10. How many license plates is that? I don't have enough room to write the number over here. 26 to the third times 10 to the fourth is
760,000.
the population of the state of Pennsylvania is about 13 million people. I have enough license plates to put a license plate on everybody in the individual backside before running out. I got plenty of license plates. I'm not worried about this. Now, again, maybe you don't work for the state. Maybe license plates don't do anything for you. You have to log into the university website, right? Every morning you get on, you got to log into MyShoe to get your email and all that crap, right? Once every 24 hours, it lets you in. How many passwords? There's a restriction to your password, right? Your password must be at least 8 letters long, uppercase letter, lowercase letter, number, all those sorts of things, right? How do I figure out how many passwords are possible? Well, again, I can do exactly the same sort of idea. But now the problem is there are more options than just counting straight through. And then, so there's a good question. What do I do with the idea of not? I'll get back to that, but there's got to be something in there. By the way, this is not actually true. You are not actually going to use all 175 million license plates, because the state of Pennsylvania keeps a list of license plates they're not allowed to make. They skip some combinations of letters so that they don't write out actual words. They skip some combinations of numbers, so they don't produce license plates with certain letter number combinations. Because right here, it would be quite possible to have some rude things spelled out in letters and numbers here, right? They do this for custom plates also. Every now and then something gets through, and it depends on where you live as to what's restricted. I found it very amusing that license plate made it through the state of Florida. 4Q. Didn't last very long once they realized what it said. The other one that made it through that really bothered me was A55RGY. And the reason that bothers me is that because in the middle of the state of the Pennsylvania license plate, we have the Keystone, right? The Keystone State. You know what's in the middle of a Florida plate? An orange. No. Just no. Again, they restrict these plates really quickly. It made it to the printer and got yanked. The NFL team jersey shop does the same thing. You can't print things if you go to buy a custom jersey for the same reason. Questions? Older computer passwords didn't differentiate between lowercase and uppercase. So it used to be that it assumed every letter that you typed in was uppercase. Well, if I'm making an 8-letter password, How many options are there?
Just letters or characters or anything?
Just letters. Now, the problem is my calculator is about to spit out something that makes me twitch my head. What's it say, Max? The hell does that mean? It means move the decimal point over 11 times. Now remember, each of these gets filled in with a 26, and I'm multiplying all the way through. So that's 26 to the 8th power. 0646. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 208 billion passwords. Just using letters. There are 10 numbers on the keyboard. If I allow myself to differentiate between uppercase and lowercase, I'd take the number of letters and go from 26 to 52. Add in the numbers, I get 62. Add in the symbols, I get another, well, let's say another dozen symbols, because some of the symbols you're not allowed to use because they mean things to the computer. So you can't use some symbols. So that would be 52, and then the 10 digits is 62, and another dozen symbols would be 74. If I did 74 to the 8th, I add 3 more zeros to that list, don't I? A lot of passwords are available. But that's only 8-digit passwords, right? What about not with 9s or 10s or 16s? So there are a lot more options. And as these get bigger and bigger, these numbers get bigger faster. Big numbers are a problem. Keeping track of big numbers is really complicated. But sometimes we use certain notations to make our lives easier. There are 8 of you. If I asked you all to line up, how many different ways could I do it? Lot. But how would I figure out how many ways I could do it? Okay, but wait a minute. I've got 8 positions for people to line up in, right? So how many options are there here? Aha. But the person who's standing here can't also stand here. So that person's not allowed to be chosen again. That person is already in line. And then these 2 people are already in line. So I lose another option, right? And I lose another option, and I lose another option. Aha. This countdown procedure happens so often, we give it its own symbol. An exclamation point. This is read as factorial. So that's not 8, that's 8 factorial. But 8 times 7 times 6 times 5, all the way down like that, that's not a small number. 40,000 something. By the way, because we use them so often, this factorial thing is built into your calculator. If you have a graphing calculator, you'll be able to find it under the math menu. So I'm going to hit the math button right here. And there's a whole bunch of menus full of stuff. Off the light so I can see the menus better. All the way on the right, the menu says PRB for probability. And there, option number 4 is the exclamation point. So I can get to that directly. I type 8, and then I go to that menu and go down to option 4, 8 factorial, 40,320. If I'm lining stuff up, if I'm making a complete ordered arrangement, this is the way I want to do it. So I'm lining up all 8. Different calculators have this button in different places, so please find yours. Deck of cards. How many cards in the deck? I want you to shuffle the deck. When you shuffle the deck, how many different ways could a shuffled deck come out? How would I change this to do a fully shuffled deck? Say that out loud, Mike. It's 52 instead of 8. That number needs to have the decimal moved over 67 times. I would like to point out to you that the expected age of the universe in seconds is only got a decimal 42 digits long. It is quite possible when you shuffle a deck of cards, you are creating someone no one ever has seen in the entire universe. Because there are more options than there are seconds in the universe. But what if I don't care about most of the cards? What if I only care about some of the cards? You know, if I'm playing poker, I only care about the 5 cards in my hand, right? Or the 7 cards, the 2 in my hand and the 5 that are being displayed, depending on what game we're playing. Well, if I want to take a subset of this, that's called a permutation. Out of some pile of objects, n of them, I'm going to pick r of them. Now, I use the word pick here to indicate that I'm selecting them one at a time and keeping them in order. And we usually write n, p, r. Sometimes people will write p of n and r, but the same idea means the same thing. I have 52 cards. If I only care about the first 5, then I can ignore all the rest of them after that. What's 52 minus 5? So I could say take the 52 orders and throw out the 47 that don't matter to me. This is 52 P5. In general, our NPR is n factorial over n minus r factorial. These are ordered arrangements. But there's one twist. If I'm playing cards, do I care what order you gave the cards to me? If I'm playing bridge, I get 13 cards. What can I do with them in my hand? I can rearrange them however I want, right? So all of those arrangements are equivalent. I use C for choose here, and my brain says, I'm going to make a C out of my hand, and I'm going to scoop them all up. So I don't care what order they're in. That means this number gets smaller. So I have to divide by how many ways I could rearrange the ones in my hand. These combinatorial formulas also show up on that same menu in the calculator, right above the factorial or NCR and NPR. So again, having these formulas is helpful, but I can do them automatically in my calculator. I can do them automatically in Excel. They're also available there. Questions? This is the end of chapter 5. So that means the homework will be two class periods today, that's Monday. And we'll actually look at what we should get based on some of these ideas for actual probabilities, because that is the whole idea, is what do I expect when an experiment is done? Probability gives me some ways to calculate that. Let's put it to better use in more standard situations. I will see you all on Friday. Thank you very much.